Friends, today we are going to discuss a very important parameters it affects on compressor performance curve. That is the parameters that includes the volume ratio, inlet temperature, pressure, molecular weight, then your compressibility factor and specific heat ratio. What is the effect on a compressor running in stages? Compressor having so many stages. What is the stages? Now stage means what is the stage consist of? Now one stage of centrifugal compressor consists of mainly three components, primary component. One is impeller, that is rotating part, another is diffuser, that is the stationary part. Along with this stationary part, what is it doing? Now it is convert the kinetic energy into pressure energy, and there and a volute which collect the, all the gases and discharge it to outside. And additionally, inlet guide vanes and shaft shields, etc. So, in the particular cases, we are going to discuss stage means rotating part and stationary part diffusers. We'll discuss. And in a multi-stage compressor, so many stages are installed in a single shaft, and then they are going to discuss here what happened when several centrifugal compressor stages are assembled together. Will the performance of one stage have any effect on the other? If one stage is any difference is there, if any change is there, whether the other stages, what will be its effects? For this reason, one by one cases we are going to discuss here. That is the one is called first one is going to discuss, that is the volume ratio effect. Suppose the compressor which is running, we decided to reduce its load by 10% reduction in the mass flow to the compressor. When and other mass flow of the fluids and other conditions mean the volumetric flow of the first stage will remain unchanged, remain unchanged. So first stage flow will drop by 10%. Since the volume flow is directly proportional to mass flow, so volume flow of the first stage will be reduced by 10%. A 10% reduction in the volume flow to the second stage will automatically be seen. When the first stage flow is reduced by 10%, so 10% reduction in the second stage is automatically seen, automatically 10% reduction will be there. However, due to 10% flow reduction in the first stage, the discharge pressure from the first stage will increase because volume flow is there because why? Now flow pressure inversely proportional to volume. Volume. This is the fastest flow, fastest flow, and when the reduction is there, then certainly the volumetric reduction is there. Certainly, inlet volume is reduced. Certainly, the pressure will fastest discharge pressure will increase, and discharge pressure increase means there is a reduction of the flow also. Reduction of the flow also. So 10% and flow in the second stage is obvious due to mass flow reduction, plus due to the volumetric 10% reduction, pressure will increase from the discharge of the increase, and proportionately the volume will decrease, and that decreased volume will go to the second stage inlet. That means 10 plus x reduction volume will go into the second stage, and then from the second stage, due to 10 plus x reduction, the 10 plus x reduction obviously third phase which will go, and when the 10 plus flow x reduction in the volumetric flow is there, then you see that again the volumetric flow will reduce, pressure will increase, and volume will decrease. So this amount will be again 10 plus x plus y will go to the third stage. So third stage, that means volume will go on decreasing, decreasing, pressure is go on increasing, and if your reduction is there, mass flow reduction or volumetric reduction is there, then compressor will go, the running point will go nearer to the surging point. Similarly, this is the original operating point. If you are increasing the flow by 3%, what will happen? The second stage in volumetric flow will also increase by 7%, 3%, because the volumetric flow and other conditions are same. So volumetric flow and mass flow are proportional to each other. So 3% reduction is mass flow, increase in mass flow, certainly increase the 10% of volume flow, 10% of volume flow. But due to increase of volume flow on the first stage, second stage inlet, first stage, there will be pressure drop. If you see the compressor, there will be pressure drop, and when the pressure drop will be there, so volume will increase. That will be increased by x. Suppose a value is increased by x. So in the second stage, 3% is already there. Plus, due to the increase of volume flow, the further volume will increase, that is x, to the second stage. So second stage volume will increase, flow will go 3 plus x. When 3 plus x going to the second stage, that means 3 plus x will go to the third stage also. It is obvious. But due to increase of volume flow, inlet of the second stage, the second stage discharge pressure will further come down and volume will increase. Pressure inversely proportional to volume. So that if we consider y, then third stage inlet will be how much? Now 3 plus x plus y. The two will go to the third stage inlet. So if you see, when you are increasing the flow, it is going nearer to the stonewall point. When you decreasing the flow, it will going to the surge point. So while running your compressor, you have to be very careful while changing the load. If you change the load suddenly, it may go to surging. If you reduce the load suddenly, it may go to surging. If you increase the load suddenly, then it may go to the stonewall. So that is the volumetric ratio you have to take care while running a compressor. Next, we are going to discuss the molecular weight. We know the head developed by a compressor does not depend on the density. So, whatever may be the fluid is, it will develop the same head. But this is your rated head. So, this is the rated running. This is the running point. Suppose we are changing the composition of the fluid handling, then higher density, higher molecular weight fluid we are discharging, then but head will remain same. But when the head remains same, then you multiply it with the molecular weight, you will get the higher pressure that will operate here. Then now the compressor will operate instead of here, will operate here, and then your reduction of the flow will take place. And it is working here, so it is going nearer to your surging point. Your molecular weight increase. Running a compressor, you are into molecular weight may increase. Suppose moisture ingress is there, some other composition gas has infiltrated in the compressor, your molecular weight increase, then what will happen? Your discharge pressure will increase and it will go nearer to the surging point. So you have to take care while running a compressor. Similarly, when your molecular weight will decrease, this is your rated, when molecular weight decrease at the head produced by the compressor same, but if you multiply with the lower molecular weight, your discharge pressure will reduce, and when the discharge pressure will reduce, volume will increase and it will go to nearer to the stonewall point. So, So, changing of the molecular weight when your compressor is running, either one stage may go to surge and another time it may go to the stonewall, depending upon the change of molecular weight of the fluid you are handling. So, while running compressor, you have to be very careful. There should not be any change in the molecular weight. There is sometimes we are spraying some water in the demister pad, so it may go inside. Your molecular weight increase, so there is chance that compressor may go to the surging. Sometimes lower gas also composition changes, so it may lower molecular weight. It can go to the stonewall point. That is to be while running a compressor. This did not happen in pump case because the non-compressible, or as it is a compressible fluid, so you have to be taking care of this molecular weight also. Now, the system resistance. Suppose your pump, and I will see the effect of system resistance, because compressor air fluids are passing through exchanger, pipeline, pressure vessels, etc. There some fouling will be there. Similarly, suction line also, there are suction demister pads are there, knockout drums are there. There also choking will be there in the demister pad. So suction pressure also may vary, discharge pressure also may vary. So accordingly, you have to change your RPM. When you are running lower RPM, simply lower, suppose you are want to run the compressor with low load, you lower RPM, is normal rated RPM, lower RPM, then you see, it is shifting towards the surging point, because the system resistance is divergent in nature. So it is the surging line, is straight line. This is divergent in nature. So it will be come closer to your surging point. If you are running the compressor lower than your surging, than your rated RPM. If you do higher, then it is further away from the surge point. That will be beneficial. Similarly, if discharge line are fouled, then system resistance will go up, because discharge pressure increase, go up, and it is coming very nearer to your surging point. This is the, if discharge lines are choked and fouled, then it is system resistance will go up. Similarly, if your inlet pressure as choked is there, pressure inlet to compressor will certainly be decreased, because inlet fluid is coming through demister pad. Demister pad is choked, so suction pressure to the compressor will decrease. This is your rated RPM, rated pressure, and will discharge pressure, suction pressure has come down. It will be now operating in this point, pressure, and it is nearer to your surging point. This is nearer to your surging point. So both suction and discharge pressure have an effect on compressor running, that you have to be very careful and check the system very well, so that so that there should not be any foul. Similarly, inlet temperature. Why inlet temperature? Because compressor are running in different seasons. In winter season, see, this is your normal running condition. Winter season, what we have done, we have seen, now that temperature has come down. When the temperature has come down, flow will certainly increase, because density will reduce, density will increase. Density will increase when flow will increase. When flow will increase, to the compressor will increase. You see, it is comfortable, because it is running away from the surge point, and your away from the surge point, but not nearer to the Stonewall point. So in winter season, why the compressor running efficiently? Because its performance curves have gone up, and it is running away from the surge point. That's why inlet temperature, you see, inlet temperature is less than the rated temperature. Your performance curve will go up, and it is away from the surging point. So your compressor running will be more stable. It can handle more fluid. Similarly, the compressibility factor. What is compressibility factor? Now, Z is equal to PV by RT, NPV by RT. That is the compressibility factor. Normal case, in the ideal case, ideal gases, what is the Z? Z is equal to 1. But when Z is less than 1, your during compression, real gases during compression often have Z is equal to less than 1. Either easier to compress, and if it is greater than 1, it is very hard to compress. So when your ZR, that is the compressibility factor, is less than rated, then your performance curve will go up. Similarly, for the specific heat ratio also, Cp by Cv signifies the impact of compressor performance influencing the pressure ratio, discharge temperature, Cp by Cv, and power required. A higher typically results in higher adiabatic temperature rise and higher pressure ratio for a given volume change, but it also increases the required work input per unit mass flow rate. So you see, Cp by Cv, this is it is the rated, and it is the Cp, it is less than the compressible, less than the specific heat ratio, then performance curve will go up. Performance curve will go up means it is favorable if you are away from the surging point, may come nearer to the stonewall point, but there is a lot of margins are there. So if your when your when your specific heat ratio is less, it is performance curve will go up. When your compressibility is less, when easier to compress a fluid, then also your performance curve will go up, and it will help you to run your compressor. They are the parameters which we need to study, need to know, need to be known before starting the compressor. And then mass flow rate. It's very important parameter, mass flow rate. Mass flow is a specific value independent of the gas properties like inlet condition. For this reason, mass flow is a specific value independent of the gas properties or inlet condition. For this reason, in the author opinion, mass flow is the best way to specify compressor throughput, how much gas is passing through the compressor when communicating with a compressor manufacturer. There are some disadvantages also, because to specify only mass flow, ton per hour or something like that, kg per hour, the manufacturer size their, but the manufacturer, why? The manufacturer size their compressor based on the volume flow, not on the mass flow. So this makes sense. Why makes sense? Because why they are manufacturing the compressor based on the volume flow? Because the size of any container is a function of volume and its content. So by specifying the mass flow, we are not able to, not covering it to volume flow, and appreciation cannot be gained for the physical size. What should be the compressor size of the compressor? We cannot come to know if you are specifying only the mass. Then it is because the manufacturer, they are manufacturing impeller or diffuser or discharge vessel, etc., based on the volume, not on the mass. But at the same time, mass flow is also important, because the same impeller for the same volume, you see, the same impeller does not care how much mass it compressing, but rather its volume. Volume, only volume it will taking care. But for example, suppose a similar size impeller can pass 4,41,000 kg per hour of propane, whose molecular weight is 4410, and will pass only 22.2 200 kg per hour hydrogen, his molecular weight 2.2 here 44.10 propane. Yeah, so propane, it will takes at least, you see the how much quantity mass it is handling, more than the hydrogen. So when you are specifying for purchasing a compressor, your mass flow as well as the volume flow is very important to have to specify. Then only manufacturer can manufacture your compressor. You can come to know what will be the size of the compressor based on the volume, and what is the quantity it will handle. That also you come to know. So when specifying a compressor for manufacture for purchasing, you have to mass flow as well as the volume flow you have to specify. Friends, I think I have covered all the topics. If you go through all the slides, your concept on the performance of compressor by changing the volumetric flow ratio, by changing pressure, inlet pressure, outlet pressure, inlet temperature, outlet temperature, molecular weight, as well as the compressibility factor, specific heat ratio, has a tremendous effect on the compressor. It is not like a pump and others. So you have to be very careful while running a compressor. Suppose for higher molecular weight, it will go nearer to your surging point. Lower molecular weight, it will go to your stonewall point. Same thing. So similarly for compressibility factor, similarly for volume ratio, similarly for suction pressure, temperature, you have to be very careful while running a compressor. If you still have any doubt, you can mail me or send me directly to talk to me. I'll certainly try to clear your doubts.